Well, thanks for coming to this third lecture on index theory. Since the last lecture was about 3 months ago, so I'm going to start off by giving a little review. So we are in this situation. We have a smooth manifold X. And I want it to be of dimension n. And we have two vector bundles over that. Let's say E and F, so vector bundles. Over X, again smooth. And then I want to define what is a differential operator of order K. Differential operator of order K. Well, it's a linear map from the space of smooth sections of one of these vector bundles into the space of smooth sections of the other vector bundle. And it should be given locally in the following form. Given by. So I want to apply D to a section F of this vector bundle E, and I want to tell you what is the value of that at a point X. And this, of course, should be an element in the fiber of the vector bundle F. Now, what I'm going to write down is a local formula. So I want to describe it locally using trivializations of the vector bundles and a chart there. So using a trivialization of the vector bundle E, I can think of the F as just a vector-valued function, right? And then using my local coordinates, I can take a bunch of derivatives of that in the various coordinate directions. So I can do alpha n times taking the derivative in the nth direction and so forth. So I take derivatives in all directions as many times as I want to. And that way I get a new section of the vector bundle E. Then I can evaluate that at the point X to get an element in here. But to think, no, I get an element in E, in the fiber of the vector bundle E at the point X. So now I want to transfer it in there. Well, so I need a homomorphism, say A sub alpha, which does the job. So A sub alpha of X is just a linear map from the fiber EX into the fiber FX. And it can depend on the point X. And I sum up over these things over multi-indices alpha, which is supposed to be smaller equal to K. And I'm also insisting, if I have an operator of order K, that some of these A's are non-trivial for norm of alpha equal to K. So that's a differential operator. So now I want to define what the symbol or the principal symbol of this thing is. The principal symbol of this operator, I denote sigma of D. So what kind of object is that? Well, this is something that I can evaluate on element xi, which is any cotangent vector at some point in X, say at the point X. And how is that defined? Let me write that here. Again, I'm going to use this local form here. Using this local form, I can write this cotangent vector xi in terms of its component. So let's say xi has components xi1 up to xin, which are just numbers now. Then I can make a big polynomial. Namely, I take alpha xi1 to the alpha 1 times blah, 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 xin to the alpha n. So that's a big polynomial function on this cotangent space. But then I put in the A alpha of x and sum up, but I sum only over those top components, meaning where the multi-index has length k. And that is, by definition, this thing. Where does it live? Well, as before, it lives in wherever that thing lives. So it's a linear map from the fiber EX to the fiber FX. So the important definition then is that D is elliptic if I look at principal symbol here and evaluate it on a cotangent vector. So this is a linear map from EX to FX. If that linear map is an isomorphism for any non-zero tangent vectors. Notice that it's a homogeneous of order k in function of the cotangent vectors. So now, of course, if I plug in psi equal to 0, I get 0 here. But I insist that this one here is an isomorphism for a non-trivial psi. That's our so-called elliptic operators. Okay. So now I want to think of this sigma d of psi in a slightly different way. I want to say what I see is a map from the pullback. So let me denote by pi the projection map from the cotangent bundle of x into x. And then I can take the vector bundle E and pull it back via psi. And I can do the same thing for F. And I claim that if you take the symbol of D, that gives you a map between these pullback bundles, which are now bundles that live over the cotangent bundle of X. Right? So why is that? Well, if you have a point here, a point in t star x, you're at a point psi. For that point psi, the definition here gives you a map from the fiber of this vector bundle at the point psi into the fiber of that vector bundle as a point psi. So all I'm doing here, I'm taking all these maps together, which depend on psi. I interpret this as a vector bundle map between these pullback bundles. So this one here is a vector bundle map. Bundle map. And this condition here that we assume ellipticity, which we'll do from now on, that just means that away from the zero section, this is an isomorphism. So this is in fact a vector bundle isomorphism when restricted to the cotangent bundle without the zero section. And that will show up a lot during this talk, so I have a notation for that. I will denote that by this little subscript 0 to say that I'm in the complement of the zero section. Okay. So why do I want to write it in this form? Well, this has an advantage that this allows me to interpret this as a K-theory element. So let me recall K-theory. So suppose that you have a topological space Y, and you have some open subset of that, say A. Then we would like to make sense of the relative K-theory. Meaning, sort of, as we can talk about relative cohomology, you can also talk about relative K-theory, that is the K-theory of this pair, Y, A. And last time I described a way to say this K-theory groups. Namely, you can represent elements in here by triples as follows. You take a vector bundle E plus, and you take a vector bundle E minus, and a map alpha between them. And so E plus and E minus are vector bundles over Y. And the alpha is a vector bundle map but you insist that this vector bundle map is a vector bundle isomorphism over the subspace. So in other words, alpha restricted to A is a vector bundle isomorphism. Then you take certain equivalence classes of these things that I explained last time, and that is a way of describing relative K-theory. So that means we can read this thing here directly as an element in K-theory, right? So this class of the principal symbol then represents an element in the K-theory of this one, of the cotangent bundle, more precisely relative to the complement of the zero section, since there we have an isomorphism. So this is the important part of this sort of upshot of this review. The principal symbol of this elliptic operator gives you an element in this relative K-theory class, this relative K-theory group. And then last time I formulated the index theorem in a way saying, oh, there's a homomorphism from that relative K-theory to Z, which was defined in purely topological terms. And the index theorem statement was that that homomorphism is the same thing as the map that associates to D the index. So this is the end of the review. So the next thing I want to do is I want to say, hey, sort of for topologists, this one here, if you sort of quotient this, not by that, since that would be non-Hausdorff, but sort of you take the disk bundle and you mod out by the sphere bundle, which is homo to be equivalent to this pair, then you get a Thom space. So we're really talking about a K-theory of the Thom space. And you know that in favorable situations, you have a Thom isomorphism there. Turns out that for K-theory, that happens if you have a spin or a spin C structure. And that's the next thing I want to discuss. So I want to talk in my second part of the talk about spin structures. And K-theory orientations. And I want to start off this section with the result that will matter at the end of the day, which is the following statement. What I'm ultimately interested in is the cotangent vector bundle. But for this discussion, I can first replace it by any vector bundle, and it can be over any topological space. It has nothing to do with the smoothness of these manifolds involved here. So let me discuss it in that context. So let's say let V over X be an n-dimensional vector bundle, real vector bundle, over topological space X. So later on, the V is going to be the cotangent bundle, and the X is going to be our smooth manifold. Then the statement is, then a spin structure, I obviously need to define what I mean by that, spin structure on a V determines a particular class in the K-theory, which is called a K-theory orientation, also known as Thom class. Tau that lives in the K-theory of this sort of corresponding pair of the total space of this vector bundle V relative to the complement of the zero section of this thing. Okay. And that in particular, and hence you get an isomorphism, and for n even we get an isomorphism between the K-theory of the underlying space X. Oh, and here I need to assume that X is a compact space. So that I can think geometrically of these K-theory groups. I have an isomorphism of that and this relative K-theory group, which is given as follows. I take a vector bundle W, right? Every element in the K-theory of X is represented by some vector bundle. And then I take this K-theory class and I can just tensor it with the pullback of W. So that's a statement of the Thom isomorphism, that if you have a Thom class, then any element in this relative K group is given as a product of that Thom class times the pullback of a vector bundle coming from the base.
What is n? N is the dimension of the vector bundle.
N is the dimension of the vector bundle, yeah. And pi is the projection map here. Everybody good with that? Okay. So now I need to, of course, explain, well, what do those terms mean? But this will be the crucial statement that will be used in the analytical part when I talk about the Dirac operator. Well, the n is the dimension of this vector bundle. And I assume that n is even, since otherwise the Thom class would live in sort of K1 rather than K0. So I'm only discussing the Thom isomorphism in this simple case. Any other question? Okay, so now I need to explain the terms that I'm using here. So what's a spin structure and what does it mean to have an orientation class? So I mean I hope that the purpose of the proposition is clear, since the index theorem, as we've seen, shows the relevance of this relative K-theory group. And so now the observation is, if the cotangent bundle has a spin structure, this proposition allows you to say, oh, the elements of this one here then just correspond to vector bundles over our manifold X. So that gives us a very good understanding of how does every element in this K-theory group look like. Well, it's basically given by a vector bundle over our manifold. That's what the purpose of this theorem is. And that will sort of take most of the talk today. All right. So, definition. What's a spin structure? So, I need to, before I delve into that definition, I need a little bit of a preamble, so to speak. So let's assume, absolutely.
The K-theory we're talking about is the complex K-theory?
I'm talking about complex K-theory. So strictly speaking, I don't need a spin structure. Spin C structure is good enough, but I want to be interested in constructing the Dirac operator in the second part of the talk. And that is much harder for the spin C Dirac operator. It needs extra geometric data, so therefore I'm interested in the stronger condition.
Sure.
Yep. So let's assume that this vector bundle V we are talking about comes equipped with V has a metric. So by that I mean, well, sort of I have a fiber-wise inner product on that, depending smoothly on or continuously on the base point. So if this were the tangent bundle, that would be a Riemannian metric on the underlying manifold. Secondly, I want to assume that V has an orientation. Okay. So then I can define this thing that's maybe called the orthonormal, the oriented orthonormal frame bundle. Frame bundle for this vector bundle V. And that's given as follows. I call it SOV, but it consists of, the following data. So X is a point in my base space X. And then I have a datum which is a frame. And a frame, in my mind, is simply a map from Rn into the fiber over the point X. So I think of that as a frame, but I want to assume that F is an isometry. So that's the orthonormal part of this. And I want to assume that F is orientation preserving. And this is it. So that's the oriented orthonormal frame bundle. I find this way of writing it convenient, since then it's sort of obvious if you have any automorphism of Rn, which is an isometry and orientation preserving, then you can precompose with that to get a new frame. So in other words, you have an action of the group of orientation preserving isometries on Rn on that. And this whole thing then is a principal bundle over X, where this projection map is given by taking such a pair and just mapping it to X. So this is a principal bundle. SON bundle, which sort of motivates this notation SOV for that principal bundle. So what is a spin structure? Here's the definition. A spin structure on V consists of two pieces of data. The first one is an orientation on V. On V. Second data is more interesting, namely, now if I have an orientation and I pick any old metric, it doesn't matter which one, then it makes sense to talk about this oriented orthonormal frame bundle, and I require that I have a covering of this. Locking myself in here. So SOV tilde should be a double covering of this bundle. So maybe I write it like that. That's my notation for double covering, okay? Okay. And one condition, namely, suppose that I look at one particular fiber here. So I have, say, the fiber, I look at a frames over a particular point X. Well, that's homeomorphic to SON, the group of this principal bundle. And then I can restrict this fiber. Let me call this P, this double covering map. I can look at the pre-image of this fiber. Now that's a double covering then, right? And I want that this is the non-trivial double covering. And I guess I'm assuming here that the n is at least bigger or equal to 2, so that I have sort of an interesting phonometric group here. So I require that this is the non-trivial double covering. Right? And there's a unique one. Okay? Well, when you do that for SON, that non-trivial double cover, is called spin n. So secretly I'm saying, oh yeah, sort of you've created a spin n at everything. So that means the fibers that I have here as fibers over X are really copies of the group spin n.
Isn't the universal cover unless n is...
Exactly, is 2, in which case, yeah, it's just a double covering of the circle. So that motivates me to call this thing here spin of S of V, since you can show that the SON action that you have here then lifts to an action of this double covering. So this has an action of spin n on it. And so this is a spin n principal bundle. Write this down. So this spin of V, if I go via projection map here to S of V, but then further on to X, this is a spin n principal bundle. So terminology typically is, so a spin structure is the lift of the structure group from of the bundle V from the orthogonal group to the spin group. It's another terminology that's done here. So I just try to say it as elementary as possible. Any questions on that?
So the orientation is not part of the data?
It is part of the data. The first part of a spin structure is you need to pick an orientation, and that orientation then determines the oriented orthonormal frame bundle S or V, and then you take a double covering of that. So it's a sort of a little two-step procedure.
I guess I'm a little confused as to what the condition is. So you're saying we can't always form the bundle spin V?
That's correct. So I'm saying the condition is that you have a double covering. Well, you always have a double covering, for example, the trivial one. But the condition that needs to be satisfied is if you restrict this double covering to any fiber, it needs to be the non-trivial double covering.
Gotcha.
And if you analyze that, you see, no, that's not always possible. And you can, in fact, relate it to the second Stephan-Whitney class of that vector bundle V. That's possible to pick such a spin structure if and only if W2 vanishes. Okay.
Can you remind me, can you have many different spin structures?
Yes. The spin structures, they form a torso for the first cohomology with the two coefficients. So if there's a non-trivial one, then that acts freely and transitively on the set of spin structures. Okay, so that explains sort of what a spin structure is. Now I want to say, well, what do I mean by a K-theory orientation? Okay, Thom class. So I have an element in here in V comma V0 is K-theory orientation. If the following condition is satisfied, so look at the pair gamma V star, then you can restrict to a fiber over a particular point x, right? So you have the fiber Vx and then the non-zero vectors in this fiber. And you have the natural inclusion map of that into that. Let's call it Ix. So that map induces then a map in K-theory going the other way. It goes from the K-theory of that into the K-theory of this pair. What does a K-theory of this pair look like? Well, it's isomorphic. I mean, this is just Euclidean space of rank n. So this is just K-theory of Rn, comma, Rn without 0. And this is isomorphic to Z if n is even, which we assume here. So, and the K-theory orientation means the following, that if you take your class tau and you move it under this map, and it goes to a generator, either plus or minus 1, then you call the tau a K-theory orientation. And this should be true for all points x. So if you restrict to any fiber, you get the generator. All x in x. Okay. All right, so now to prove the proposition, we need to sort of construct these classes, right? So let's first talk about this one here. So we want to construct for even n a generator of this relative K-theory. And we know what it looks like, right? It's given by a pair of vector bundles over Rn. Well, that's pretty boring, right? They're all trivial. And I need a vector bundle map between them, which should be an isomorphism away from 0. That's sort of how we represent elements in here. Now, there is a simple way of describing it, but I want to do a slightly more advanced way, which will help us to move that construction to the parameterized version of that. And that construction is in terms of Clifford algebras. So I first need to say, well, what do I mean by a Clifford algebra here? Okay. So it goes like this. So Clifford algebra Clifford n is defined in the following way. So I first take the tensor algebra that's generated by the vector space Rn. So in other words, I take Rn, and then I take a whole bunch of tensor powers of that, and I add them all up. So L goes from 0 to infinity. So this so far is the tensor algebra generated by Rn. The Clifford algebra is a quotient of this, so I mod out by a certain ideal. What does that ideal look like? Well, I first can take for any element, say psi in Rn, I can take psi tensor psi. That's a particular element in that power 2, right? And then I can add to it another element, which is just the norm of psi squared times 1. So that sits in the sum at L equal to 0, which is just a copy of R. And I take the ideal generated by that, mod that out, and that's a Clifford algebra. Okay? So this is it's actually a finite dimensional algebra. It's an algebra of dimension 2 to the n. So it's the same dimension as the exterior algebra, which would be the thing that you get by modding out by all those guys. This is just sort of a deformation of the exterior algebra. Okay. So now suppose, so what is the structure that you have here? Well, the tensor algebra is a Z-graded algebra. Now here we mod out by an ideal that is something of degree 2 and something of degree 0. So no, the quotient is no longer Z-graded, but it still is Z2 graded. So this is a Z2 graded algebra. Which means in particular I can write this thing as a sum of the plus part or even part and the odd part or minus part. And that just corresponds to, well, the product of, do I have a product of odd number of elements, or a product of a product of odd number of elements, or a product of an even number of elements. That determines where these things live. Okay. So now what does it have to do with this one here? Now I want to take a module. So let's say lambda, and it should be a Z2 graded module. So it decomposes into a plus part and to a minus part. Should be an irreducible Z2 graded module over this. There are two of those, and so the Ktheory element that we construct at the end of the day, the sign of that will depend on which one we took. But you can make some convention about that, but for our discussion it doesn't matter. So then what do you do with it? Well, so by definition, this algebra then acts on this one. Now, inside Clifford n, inside the tensor algebra, you have Rn sitting as the degree 1 part of it. It turns out that that embedding survives to an embedding of Rn as in the Clifford algebra. So this map that I have from Rn into the tensor algebra, if I compose it with a projection map from the tensor algebra to the Clifford algebra, survives to be an injection. So I have an injection of Rn into that. And in fact, since these are tensors of one element, this is in the odd part of the Clifford algebra. So I have Rn tensor lambda sitting inside the odd part of the Clifford algebra. Now, if I take an odd element of the Clifford algebra multiplied by an even element of my module, I get an odd element of the module. So in particular, then, I have a map from Rn tensor the plus part, the even part, into the odd part. And this is the central map that we'll make good use of. So this is called C, I'll denote by C, and this is called Clifford multiplication. So believe it or not, but this is a very important ingredient of the constructions that I'm going to do. Any questions so far? Delta is an irreducible Z2 graded module over this Clifford algebra. Any other questions? All right, so now let's make use of this stuff. So I want to write down the generator of the K-theory of Rn, comma, the non-zero vectors. So for that, I need to write down two vector bundles over Rn. Here are my two vector bundles. I take Rn cross delta plus, and the other one is going to be Rn cross delta minus. So these are my two vector bundles, and now I'm looking for a map. Gee, what could be the map? So I have a vector psi, and I have a lambda in here. I want to make something out of that which guarantees that what I'm writing down is linear in lambda and should be invertible if psi is non-zero. Well, you Clifford multiply those two things. That's why I defined that, right? So of course here needs to be psi since it's a vector bundle map. But here then you take the Clifford multiplication of the vector psi and the element lambda. Okay, so let me call, I'm using notation, I just write that. That's for me is Clifford multiplication. So that's a map. And why is that an isomorphism if psi is non-trivial? Well, if you look at the relations, this is saying psi squared this is psi squared, is equal to minus norm of psi times 1. Oh, so if the norm of psi is non-zero, then that means that psi divided by norm squared of psi is the inverse of psi, or minus that is the inverse of that in the Clifford algebra. So therefore, I can just multiply by the inverse. So therefore, no, of course, it's invertible then. Okay, so this is, in fact, and then you can show this is a generator of this K-theory group. All right, so now we want to generalize that and make not just the generator of this group out of it, but we want to use it to produce a generator of this group here. Okay? The crucial thing that we need for this one here, so the key fact is that this Clifford multiplication is spin n equivariant. Now, at this point, this does not make yet sense, right? Since spin n was described very abstractly as just the non-trivial double cover of SON, why should that act on the lambda, right? That's not clear at all. Well, there's a... Absolutely.
I'm a bit confused since we're using delta to be any reducibles into.
Yep.
And how do we know one exists?
Well, you need to understand what this algebra is in an explicit form, and then you can prove that you have exactly two irreducible ones for n even, which I'm always assuming now. Now you could ask, well, okay, so then do you get the same generator, independent of which irreducible do you use? The answer is no. You get the negative of the other generator. But no, okay, so no big deal. Just make a convention and take that one. Okay. All right, so what does this spin n equivariant means? Well, I'm going to give you a different construction of the group spin n in terms of Clifford algebras, which will involve that one. So how do I do this? So I start with the Clifford algebra. And I take the group of invertible elements of the Clifford algebra, and I define spin n to be a subgroup of the invertible elements in here, which are generated by the elements psi. Sorry, no, this is not spin n, this is pin n. Sorry, pin n. It's generated by the element psi, which are unit vectors inside Rn. And remember, Rn is sitting inside the Clifford algebra, and any non-zero vector, in particular the unit vector, is invertible. So yeah, these are elements in the invertible part of that. So then I can say, well, take the subgroup generated by that, right? But now to convince you that this is any good, I need to show you, well, what's the relationship between pin n and on, right? So I better show you that you have a double covering here into on. How is that supposed to work? In particular, well, if you have a psi here, one of these generators, these unit vectors, well, how do you get out of a unit vector an element from on? Well, you can probably guess it, right? Take the reflection at the orthogonal plane, right? So you map this one here to the reflection at the plane orthogonal to this unit vector, and that's an element in on. And that gives you a homomorphism from this group to that. Now, this is not a proof, but notice that there are two element psi's here that go to the same reflection. Since whether you take psi or minus psi, well, it goes to the same thing. That strongly suggests that, yes, you constructed a double covering this way. And yeah, you can check that this constructs a double covering. Well, if you have a double covering of on, well, then you get a double covering of SON by restricting to the part that's sitting over SON, right? So then you define spin n to be that appropriate part. Now, how do you recognize whether you get an orientation preserving isometry? Well, it depends on how many reflections you have. How many reflections you have, well, that reflects a parity, whether you're in the even or odd part of the Clifford algebra. So in other words, you just take the group pin n, but you take only the even part of it, in the even part of the Clifford algebra. And that's on a double covering of SON. Okay, and now this makes sense, right? Since how does spin n act on this one? Well, spin n projects down to SON, and SON certainly acts on Rn. How does it act on delta plus or delta minus? Well, spin n by construction sits inside the plus part of the Clifford algebra. Clifford delta plus and delta minus both are modules over the even part of the Clifford algebra, and then you just restrict to this subgroup of the invertible elements of that even part of the Clifford algebra, and so that way these things act on that. So that was probably quite a package. Any questions on that?
So you're saying allow spin n to act simultaneously on Rn and delta?
Yes, I allow it to act as in all of those things in the prescribed way, and then I'm saying, oh, then the whole map, this Clifford multiplication, is spin n equivariant. Thank you for the reminder. Yes. So the question was, so when you talk about the spin n equivariance here, do you mean that you act on each of these components, on Rn and delta plus and delta minus in the prescribed way? And the answer is yes. Thanks for the reminder.
Another question. When you say there are two C's on the board, one C goes from Rn tensor delta plus to delta minus.
Yes.
The other C goes from Rn cross delta plus to Rn cross delta minus. Which is the one that we're asserting is spin n equivariant?
This is the thing that I'm asserting is spin n equivariant.
Very good.
Yes. So the question was, there are two C's on the board, namely this one and that one. Which one are we asserting? And the answer is, yeah, I'm asserting it's for this one as being spin n equivariant. Okay. So what does the spin n equivariance of this map buy you? It means that you can do something at the level of vector bundles. Namely, now use the fact that V has a spin structure. So that's an assumption, right, that we made in our proposition. V has a spin structure. So that means what? Well, this means that this vector bundle V, this means first off, I can construct this associated principal spin n bundle, right? Let me call this P for simplicity. That's a principal spin n bundle. And spin is n is a long word, so let me abbreviate that with G. Now, if I have this principal bundle, now how can I recover V? Well, I can recover V by saying that's an associated vector bundle. I mean, I take this principal bundle P, and then I take the action of spin n on Rn. That way I can recover V. Okay, so why is that helpful? Let me write this down here. So I want to get mileage out of the equivariance of this Clifford multiplication map. Okay. So here's what I can do, is I can say, okay, each of these vector spaces, Rn and delta plus minus, are representation of my group G equal to spin n. Then I can form the associated vector bundles. So I take P cross over G with Rn, tensor with P over G cross delta plus into P cross over G with delta minus, where this map is just given by doing the identity on P and just taking the map C on the fibers. So what I'm saying is whenever I have an equivariant map between representation, that produces a map between the associated vector bundles. So I get a map like this. But now I can identify those things. So this one here, by the remark over there, is just our old vector bundle V. This one here, yeah, that's a new vector bundle. This is the so-called spinor bundle. So this is the spinor bundle S plus, and this is the spinor bundle S minus. These are so-called spinor bundles. So the upshot is that the equivariance of this Clifford multiplication map allows me to construct a map, a vector bundle map from V tensor S plus into S minus. And now I'm going to use that map the same way as I did use the Clifford multiplication before, right? So I write down S plus. I write down pi star S plus. So that's now a bundle over the total space of my vector bundle V. Same thing, pull back S minus to the total space of V. And there I have this map given by Clifford multiplication, or written down more explicitly. What's an element in here? Well, it's a point in V together with a lambda. And then I can just map that to the same point psi, but I take the Clifford multiplication of this vector psi with the spinor lambda. Okay. And then this one here is an element in this relative K-theory of V comma V0. Right? Since, yeah, the Clifford multiplication was an isomorphism whenever the psi is non-zero. So yeah, it's an isomorphism away from the zero section. And then by construction, what we did here was just sort of, well, we did in every fiber what we did before to construct the generator of Rn, of the K-theory of Rn, comma Rn minus 0. So by construction, the restriction of this particular tau to each fiber is going to be the generator. So this is a Thom class. So is a K orientation. Okay, so that sort of shows the construction, and that's the technically hard part of the thing. So now I have about 5-6 minutes left. So now comes it. Absolutely.
So how is there a complex structure on the spinor bundle?
Yeah, I should have been more precise. When I talked about irreducible modules here, I meant irreducible modules over actually the complexification of this one here. Sorry. Yes, I did not write this down correctly. Thanks very much. So the question was, well, why do I have a complex structure on these spinor bundles? Well, yeah, that should come from a complex structure on delta. Well, that's how I choose it. So you can do this whole discussion in terms of modules over the Clifford algebra itself, the real Clifford algebra, but that is more complicated since there's an 8-fold periodicity going on in terms of n instead of just a 2-fold periodicity as in the complex case. All right, so now let me go to the bonus third part of the geometric thing. Now the obvious question is, namely is, well, gee, so this K orientation is sort of the mother of all K-theory classes in this K-theory group, in the sense that every other class is obtained by just multiplying by a vector bundle from X. So then this corresponding question is, well, then there's a mother of all operators, right? Namely, an operator whose principal symbol is the k orientation. And that operator is called the Dirac operator. So that's what I want to do in the quick third part. Which is on Dirac operators. Okay, so we have our smooth manifold X, and now we want to assume that X is actually a spin manifold, spin n manifold, with the Riemannian metric, of course. And what does spin n manifold mean? Well, spin was something that we previously applied to vector bundles, so that means, in my mind, that the cotangent bundle of M has a spin structure. Okay, so then how can we write down an operator? Here's what we do. The most important part is you use the Riemannian metric to argue that you have the Levi-Civita connection on the tangent bundle of M. And tangent bundle. And that has the effect that this induces a connection nabla S plus on the spinor bundle. So this is a little technical to describe, since on the way from the tangent bundle to the spinor bundle, you dive through principal bundles. So you need to talk about connections on principal bundles, but it's not very complicated once you know what a connection on a principal bundle is. Anyway, the upshot is you get a connection on this vector bundle of spinors. Okay, well, then you can do the following. So take the sections of your plus spinor bundle. Then you have a connection on that. So what is a connection? Well, one way to think of a connection on a vector bundle, it's a map from the sections of the vector bundle to the sections of the cotangent bundle tensor the original vector bundle. Right, since if you give me any tangent vector, I can evaluate this section on this particular tangent vector to get an element in S plus, and that's sort of like the derivative of the original section in the direction of that tangent vector. So that's how I wish to think of connections. Well, let's see. So this operator can't be elliptic, right? Since this bundle has a much higher dimension than this bundle, and ellipticity can only work if domain and range bundles have the same dimension. So you need to come back to something which has the same size as S plus. That's where your Clifford multiplication comes in. So you use the Clifford multiplication for the cotangent bundle now, and you say, well, okay, go back here. That's it. That's the Dirac operator. Now you write down what is the principal symbol. Yeah, I should give this thing a name. This is sort of the typical physicist notation for that. This is a Dirac operator. And then the principal symbol of this Dirac operator, that's exactly our Ktheory orientation in the Ktheory of the cotangent bundle of X relative the non-zero vectors. Okay. So the Dirac operator in that sense is the mother of all operators. Well, now this does not cover every element in here, right? But remember that every element in here is obtained from this class by just tensoring by a vector bundle. So now suppose you have a vector bundle W over X, vector bundle. And the first thing you need to do is, well, you pick a connection on that. So with a connection, nabla W. And the operator that I'll write down will depend on that connection, but the principal symbol as a Ktheory element will not. So then you can do the following. So you basically repeat the previous construction, but with a slightly bigger bundle. Maybe you tensor your spinor bundle S plus with this vector bundle W. And hey, you have a connection on this bundle, you have a connection on that bundle, then you also have a connection on the tensor product of these bundles. So just let me denote it nabla S plus tensor W. That brings you into the sections of the cotangent bundle, tensor, that whole stuff. But now you want to cut it back to size, well, you use the same technique, right? Since you have a map that contracts those two things, and you don't do anything to W. To go back to the sections of S minus tensor W. And this is called the notation for that is typically like this. And this is called the Dirac operator. Twisted by W. And yeah, then the principal symbol of this one here is what you would expect. Namely, it's just the product of tau times pi star W as an element in the K-theory group. So what's the upshot of all this? Well, if you're only interested in the K-theory class of the principal symbol of operators, which is everything that the index depends on, then you might as well restrict your attention to twisted Dirac operators, since up to they have the same every operator has the same principal symbol as some twisted Dirac operator, right? So that's why in the next and last lecture I will talk about only what is the index for twisted Dirac operators, and I will write down an explicit formula in terms of the Aruf genus and the chunk character of the bundle we're twisting by. Any questions?
I don't have like broad philosophical questions, but just have like questions about the lecture.
Mm-hmm.
Are there too many P's, in this map over here? So like on level of fibers, like you take an element of Rn, an element of delta plus.
So you're talking about this map here, which map? The map up there.
Yeah. So like, okay. Are there like too many
Okay. So what I need to do is, I look at, yeah, so one thing I can do is I can say, oh, this associated bundle, so the question was, how do I get this map, right? Yeah. So one observation is that the tensor product construction is compatible with the associated bundle construction, meaning I can rewrite this as saying, oh, I take the representation of G that's given by the tensor product of the representation Rn and delta plus. So I can write it like that. And then the general statement is, oh, the associated bundle construction is compatible with tensor product. So if I take the tensor product and representation of representations, form the associated vector bundle, that's the same thing as the tensor bundle of the associated vector bundles. And so then it's just a matter, okay, if the map from this representation to that representation is equivariant, then I'm good. That induces for me a map between associated vector bundles. Yeah, no, this is not external. This is over the same base bits. It's over X. Any other questions? All right, thank you.
You mentioned that preferred algebra is a document transformation of exterior algebra.
Mm-hmm.
How do you see that?
Well, the best way to do that is to give a slightly more abstract definition. So I will just write this down in a sec. So what is the input needed to define a Clifford algebra? Is you need a vector space together with a quadratic form on it. So V, and we have a quadratic form. Quadratic form. And then you do the same thing. You take the tensor algebra generated by V, and then you mod out by relation. And the relation is you define V times V to be equivalent to Q of V times the identity element. So, well, if you take your quadratic form to be identically 0, right, then this is saying, oh, you said V times V to that, and you get the exterior algebra. If you take, on the opposite side, some non-degenerate quadratic form, then you get exactly the Clifford algebras. Mm-hmm. Any other questions? All right, thank you.